And we're going to talk about bug mining, or industrial bug mining, aka fuzzing. So the reason we call it bug mining is it turns out to be one of the few analogies I've come across in security which is actually worthwhile. And the reason we call it industrial is because these days finding bugs is something that has a commercial return. It used to be you'd find bugs for fun or whatever the hell, but now that the markets are much more defined, they're getting closer to, you can put a value on certain grades of rootite, like even if it's not a confirmed exploitable bug. So to do it for money, you want to do it like the mining companies do, okay? You start with large-scale extraction. Running your one fuzzer on your one laptop does not cut it these days. After large-scale extraction, you get left with masses and masses and masses of crashes. I work mainly on Word. It's a strange perversion I have. And we'll see some numbers later about the numbers of crashes or bugs or exception events I've got. But it's a lot. So then you have to move into grading, where you need to work out, okay, on which of these bugs do I spend some time? When you're on attack, as in when you're trying to commercialize bugs for some kind of return, you have the problem where you need to work out which bugs are useful, which bugs are going to be exploitable, because a non-exploitable bug is useful to Microsoft but is not useful really to anyone else. When you're on defense, it's like you have the luxury of just being able to fix them all, right? So that's the grading phase. And then I'll talk about some ideas I've had for enrichment, which is to take non-exploited bugs, just crashes effectively, but to give people more information. Like when we pass them over to someone that exploits, to like exploit guy, to give him a bit more of a head start so that he can hopefully get an exploit done faster. Because the less time exploit guy spends exploiting this bug, the more time he's going to spend exploiting the next one, which again increases your total return. And then phase 4 and 5 I'm not going to talk about in this talk, but obviously those are the natural corollary of doing it as an industry. Like something happens and then there's some kind of profit. So let's talk first about extraction, which is fuzzing, but fast. So now I talk about mega tests. That's going to fall off. So in 2009 we built a distributed fuzzing farm. We used 8 servers, 8 physical boxes. That's 64 cores. And so I took my initial fuzzer that I wrote on my laptop, which does about 30-45 tests per minute, and I scaled up to 30 tests a second, which at the time I thought was pretty badass. Like I was happy with it. So then in like April or so, Tom and the office guys build this like DFF, distributed fuzzing framework, which is an amazingly like imaginative name, by the way. And they got up to 12 million iterations in a weekend, which is like 6 mega tests a day. But now it's faster. Now it's more like 10, unless it's faster again. No, say 10 mega tests per day. So I got pissy because, you know, like I released some numbers and then they released better ones. So we stripped the whole thing down, rebuilt all the software, optimized everything. And now we're doing about a tick over 1 mega test per hour. That's 1 million tests, file fuzzing tests per hour, which is, you know, for me kind of fast. Like I'd like to go faster, but that's what we can do with the current hardware, which is what, twice as fast as, I don't know, whatever 1,000 machines Microsoft are using on 8 old servers. And it's all about scale. So what you don't have when you like write your first fuzzer on your laptop is a scale problem. And then you go and you parallelize and you might use 3 or 4 laptops and you still don't have a scale problem. Like whatever parallel thing that you wrote in Twisted is like, hey, that's totally fine, it scales perfectly. But when you're scaling across, say, 90 plus VMs or 90 plus fuzzbots across 64 cores, you suddenly start coming across all these problems that you didn't have before. You've got to look at your serialization layer, you've got to look at your distribution layer, you've got to look at the whole architecture of, like, can I even ship the tests to the boxes that fast, let alone whether they can process them that fast, right? And so you need to work bottleneck by bottleneck, network, I/O, layer, code, until ideally what you would like to be bottlenecked on is just cycles spent on the specific code that you're trying to fuzz. So not just CPU cycles. What I would love is just cycles spent inside MSO or WWLib. That would be perfect for me. So if we look at the scalability that we have with the current bug mine, the marketing guys would draw it like this. The numbers don't matter, but this is the scale starting at 8 cores on the left-hand side, going up more or less arithmetically to 64 cores where the dotted line is. And then after the dotted line, we hit the wall. But I keep going because some spare capacity is useful to soak up extra tests. Like sometimes there's a test that's going to make a machine hang. So that bot is sitting there not using CPU, but hung trying to allocate memory or something. So those cycles need to be soaked up by a spare bot. So as long as it stays more or less flat after the cutoff, then I'll do that. So yeah, this is like the marketing version of that, of like that scalability. Woo, epic, red line goes up. And this is how I would draw it as an engineer, which is a less good line. And this is the tests per second per core. And unfortunately it goes down. Like, I would like it to be flat. So it's not perfect, but it still like tops out at over 300 tests a second, which is okay for 64 cores. But yeah, unfortunately, still not like perfect scalability, but kind of good.
Okay. Can I ask a question?
Sure.
Hey, so when you're like, when you're popping up Word, for example, right, you're fuzzing it, isn't there some like wasted time when Word comes up and you give it a file or something? Or how are you dealing with like the 5-second delay, or if you're using virtual machines? Because that seems like that would, I don't know how you're getting like 1 million tests per second or whatever out of, with that type of delay.
With magic. No, I'll talk about that. It is an excellent question. The question, if you didn't hear it, was like, why aren't you wasting like seconds with like just opening up the Word interface? And I'm not. But we'll talk about it. So what do we do? How did we build it? Initially, I built on ESXi, which turned out to be, for me, not such a good idea. Like, it's free and it's worth every cent. The performance of ESXi is kind of good, but the management is a complete pain in the ass. So we moved over to KVM, which is just running on real Linux, and we're comfortable with Linux. Like, we've used it before, we can monitor it, we can manage it, and it's almost as fast. Like, I haven't done benchmarking because it's very difficult to know what to benchmark when you benchmark ESX versus KVM. But anecdotally, I've never seen an XP box boot up as fast as the VMs do inside the KVM, so it's good. The storage, we moved off to a dedicated storage network, so that's a separate switch. It's a managed switch, so the sandbox has 4 NICs going into that are teamed. OpenISCSI, free again. We striped a bunch of SSDs, so that's like IOPS out the butt. It's like crazy, crazy fast. We ended up using Oracle OCFS cluster file system. We tried the Red Hat GFS or whatever the hell it's called, but it's horribly, horribly, horribly broken. I assume that they break it so that they can sell Red Hat support, but yeah, don't do GFS. I optimized the harness as much as I could, which I won't talk about. Like, Ruby is already pretty slow, but it turns out that's not really my bottleneck. And you want to optimize your fuzzbots. So there's a lot of information that I didn't put in this talk because I talked about it in 2009. So if you really want to know how to set up an optimized fuzzbot for Office, then go read those slides. One thing that you might want to do is actually kill explorer.exe. That's the shell that gives you the start bar and all that crap. Because it turns out when you open lots and lots of files really fast for a long time, that starts to bloat and will end up taking most of your CPU and most of your RAM. And you can run quite comfortably without it. You've just got to like bring up Task Manager to start new processes. And to answer Jared's question from before, I do not open a new Office process every time. So this is the thing that's like potentially contentious. Like it's kind of cheating. So if I open the file successfully and the OLE call returns, then I say that's good to reuse. If I try and open a file and it returns an OLE exception, which means it's popped up a dialog box that says this file is corrupt, I dismiss that dialog box and I still call that word safe to use. And I just have a 2% chance that I'll like kill it off and open a new one to stop it, like, because otherwise you leave them really, really long term, the word process itself will start to bloat, and once it bloats, it runs a lot slower. So the downside, I guess, like the aesthetic argument would be that, hey, if you're leaving this word process open, then there's going to be some like wacky heap stuff. So you're either going to get bugs that are going to be hard to repro, or you might even get bugs that you wouldn't otherwise have got. So I'm running with full page heap, which takes care of a lot of the heap AVs. And say I get a bug that's hard to repro. If I can't repro it, I'll just throw it away. It's not like I don't have enough. Like this would potentially be an issue for like a QA team or for Microsoft, where they want, like, oh my god, we've got a bug we can't repro, like something's gone wrong and we cannot make it happen again. But for me, I don't call it a problem. And it's like, seriously, almost 10 times as fast doing it this way. Which is kind of the reason I like don't jump up and down and brag too much about how much faster I am than Microsoft, because I know for a fact that they don't do this. So they've got like a 10 times speed up in their pocket that they're not using. They're just waiting for me to taunt them. Some of the stuff that KVM gives you, KVM I find is awesome. So the provisioning is super easy. Because everything's on a shared iSCSI disk, we use one template. On top of that template, we use what are called, like KVM call them overlays. VMware people would call them linked clones. It's just a difference disk from the template. Then on top of that, we run in snapshot mode. And what snapshot mode does is take the differences from the difference disk and keep them in tempfs. And tempfs, as long as you've got RAM, is going to be in RAM. So A, completely fast as you can go. And B, as soon as you turn them off and on, you get a brand new, shiny, clean fuzzbot, completely defragmented, ready to go. So if ever things are going slow in a fuzz run, turn them off, turn them on, brand new and shiny. I can make template changes in minutes, whereas before in the ESX stuff, like copying stuff around out of VMFS is super slow, because VMFS is not meant for that. So I had like, seriously, like when I was copying full disks, 24 hours to re-provision a brand new fuzz template, which sucked. The management is, for me, easier and much more powerful, assuming you like Bash and SSH. And let me tell you, when you're VPing in from Kathmandu, you really like Bash and SSH. You do not like VNC. So yeah, no money on software, apart from, you know, me and I work for beer. We're using MSDN licenses for Windows, so that's like a price may not apply. And we reckon like about 30K for the hardware. So if you like, when we get on later to the numbers, you can all start like doing the mental maths and work out how much per bug, and you'll find that the return on investment is actually fair. And it looks like this. Well, it doesn't look like this. A diagram of it looks like this. What? This is my elite graphic design, man. So the boxes marked A are producers. These are logical components. The producers can physically be on the main hardware, or they can be separate boxes. At the moment, I have them as separate boxes. I can have as many boxes marked A as I want, as many producers, and I can run as many actual case generators as I want. So I can run 5 different algorithms for case generation side by side, and they all feed into this guy B, which is the fuzz server. So the grey lines sort of separate out physical components. So B, the fuzz bots, like the stuff in 2, and C are all running physically on the same server, share and cause. Not only that, I can, I guess I'll talk about that later, but I can fuzz multiple products. Because the A guys, they tag their cases. So I can dedicate some fuzzbots to fuzzing Word, and some to fuzzing PowerPoint, and some to fuzzing OpenOffice or whatever the hell. So the A boxes deliver to the B. That does the delivery to the fuzzbots, and all of that is internal to that machine, so there's no actual physical network access at that point. So that cuts down a bottleneck. The result goes through to the analysis and storage layer, which is the C component. And that component is in charge of what to do with the data. And it can either stuff it in a database, or it can stuff it in flat files or whatever it wants. And I can change that on the fly. I can change that at runtime. So at the moment I'm storing flat files and post-processing for a database because it turned out to not be useful and fast to do that inline in real time. And then I stick them into a database later for the data mining. But I can do it inline as well. I've got the code. I just took it out to make it all work. So it's a pretty simple architecture. B and C are in Ruby. That's my code. That's written on Event Machine. A does not have to be in Ruby. A could be in any language you want. And anything in 4, which is the backend, again, could be anything we want. Right now I'm using PostgreSQL because last time I was using SQLite and Dave laughed at me. So I changed. So software hot swap means that I can take out any of the components. As long as the case generator is still active in memory, I can change the distribution layer, I can change the backend, I can turn the fuzzbots off and on, whatever, I will not lose a case. The only thing is when the power goes out in Singapore, then I'll lose cases. Tagged queues I mentioned before lets me fuzz multiple products at the same time, all through the same middle infrastructure. And any case producer front end means you can use Python if you're one of those sick freaks. You could use Perl, anything to make your cases and feed it all into the same harness. And everything scales as best I can horizontally. So N producers, N distribution nodes, N backend nodes. So we're across 8 physical servers now, but we can literally just chuck another one in the rack. When we were doing the migration, what I was doing was taking one of the disks out of server 1, sticking it in, DDing it onto the disk in server 2, and he's good to go. Before I move on to the next bit, which is the amusing bit, are there any questions on the architecture, how it's built, how it works, why I'm an idiot, or? Hey. Yeah.
I'm just curious, do you write your own test generator, your case generators, or just tend to use off-the-shelf?
Okay, so the question is, do I write my own case generators? Yeah. I recently did a little bit of research on the methods of case generation and which ones prove the most effective, which is on the Daily Dave list. And it turns out that the stupid generators are not as useless as you would imagine, and the smart generators are not as awesome as you would imagine. But the general impression is that you're going to need, in my opinion, to do some stupid stuff, find out which areas crash a lot, and then zoom in on those with smarter stuff. But yeah, no, I write all my own stuff because as best I can tell there is no, every fuzzing guy writes their own framework because everyone else's framework sucks and we all think the same thing. And sorry?
Apologies if you mentioned this at the beginning, I underestimated the distance from the end of the corridor to here. How many KVMs per core are you able to get?
Right.
Are you bounded by CPU or RAM?
Yeah, I won't go back to the slide. 1 per core is optimum for performance when everything is going well. I stretch to about 1 1/4 or 1 1/2 per core, RAM allowing, so that there's excess capacity for machines that go idle for a while. So to max your CPUs, when all is going well, 1 per core, but add a few more. Don't try and go more than 1 1/2 per core. That just doesn't work.
And do you have a problem where you run out of TempFS?
Do I run out of TempFS?
Suddenly explodes for some reason.
Yeah, right. If I ran out of RAM for TempFS, I'm led to believe that Linux will do the right thing and not segfault. It'll probably just put it on disk, so that should be okay.
Thanks.
Yep.
How do you handle when the CPU may be pegged at 100% for a while? You kind of touched on it a little bit, but do you
convert it to a snapshot? Do you have
Yeah, right. So the question is, like, how do I deal with when a fuzzbot gets a test that makes it go crazy, like pegs the CPU of the VM? And that's a very common problem. So I have, this is like, if you're interested in that, you should look up the slides from SciScan last year when I talk about all of this stuff. But I have a Reaper process which I start at high priority, like Windows high priority, which looks for long-running processes, like processes that haven't done stuff for a while. So I don't directly check the CPU, but the same thing will work for memory bloaters or just hung for no reason or whatever. And that Reaper is effective in, say, 99% of the cases. Then about 1% it goes unbelievably crazy, and then I have a last chance that'll kill the debugger that's attached to the process, and that kills it for sure. In that case, I might only get like partial crash data.
Back to my other question. So you leave Word up, I got that, but you still have to be able to tell either when it's done processing or wait some amount of time, right?
Ah, right. Yeah. This is the how do I detect successes problem. Like a big problem when you're instrumenting something is like, how the hell do you know when it's dealt with your test? Which is a huge problem for a lot of apps, but not so much as it turns out for Office apps. Because Office apps I can invoke with OLE. And the OLE call will actually return as soon as the document has opened, or to return an exception as soon as it's detected corruption. The only time where I've got to like wait is when it's like crashed or faulted and it's gone to the debugger. So with Word you get like an advantage for that.
So your framework is pretty specific to Office, and it wouldn't do well with Adobe or some other.
Anything that's like can be invoked via OLE, but yeah, for like stuff that won't speak OLE at the moment, I would need like a different way. Like I wouldn't just use a timeout because I'm not that lame, but I haven't had the problem yet.
Right. CPU, I think, is the only thing you can do other than unless you can have some callback.
Yeah, no, it's an ugly problem, that's for sure. Okay, so now we're going to talk some about grading. Oh, sorry, one more.
Yeah, Ben, I have another question for you. So, why use VMs in the first place versus, say, application virtualization or even OS virtualization, where far less overhead and
Right.
why the choice to use VM?
Yeah, that's so it's like, why am I using like a whole VM when I could like virtualize the app? Word doesn't actually run that well in like Wine. Surprise, surprise. We looked at it when we were doing the run tracing, and it turns out it's like a fail. Like it'll sort of run, but you try and run it under Valgrind, which we thought was going to be the best thing ever, and no.
SoftGrid and Virtuoso and a couple other things out there.
Yeah, maybe. I don't know. VMs work is, I guess, the short answer.
And you're right, KVM snapshots are very cool.
Yes. So, okay. So here's the thing. So we're in like Hangzhou, China a few weeks ago, and like we're out drinking with Tom from Microsoft, and my boss plays like a game of pool and bets, like, which I think is unwise, like betting on pool from a guy from New Orleans. And so he, of course, gets his ass kicked, and the bet with Tom was for Ode. So now we owe like Microsoft some Ode. So yeah, I choose to pay now. So we're going to talk about bug triage, which is how you take your Bang exploitable output and work out if it's actually worth spending time. So I'm going to take a few bugs just for tutelary purposes. And these are all Word 2007 examples. So this is the current corpus. This is a couple of weeks worth of fuzzing with various case generators. So that's 60K-ish crashes, broken down by Bang exploitable classification. So only like 1,200 or 1,300 are rated as exploitable. 621 buckets. I don't know if you guys already know how Bang exploitable works, like, well, at least one guy does. But it basically looks at how we got here, and that's more or less all it looks at. It doesn't look at, like, what does this crash look like? So those buckets are not going to be issues. In fact, of those, only 373 are unique EIPs. And even those are not going to be issues, right? Because if EIP's gone crazy, you're going to have like 20 EIPs from one bug, effectively. So there's 88 buckets of exploitable and 110 buckets of probably exploitable, and then some potentially like unknown and probably not. But it turns out, as we'll see, that you can't trust the classifications that much. Like, bang exploitable is awesome, like it's fantastic for crash binning, but it's not like don't take its word as gospel. So for example, this guy is called exploitable because it's a user mode write AV, and I don't think it's unreasonable to call all user writes exploitable. But assuming that I can control ESI, like you see we're moving BL into ESI plus something. So assuming I could control ESI, then I can write a null byte somewhere. So like Kostya or Skylar or Mark Dowd might be able to exploit this, but I freaking can't. Like, even if I've got full control over ESI, right? Like I can truncate a function pointer maybe and like end up having it go somewhere else. But honestly, like, I have better things to do with my life. So it's the kind of bug you'd want to fix if you're Microsoft, but it's not the kind of bug that you'd want to like say to your exploit guy, don't come back until this bug is exploited.
You want bang exploitable to say easy to exploit, hard to exploit, but it's still exploitable.
Yes, that would be good. Can you do that? Is that all right?
I'll put in the feature.
Whereas this one is probably exploitable, where I don't know, like, for me, this is a much more interesting bug than the last one, right? It's like basically call EAX. It's called EAX plus 28. So this is like getting towards awesome, because you now have direct control, assuming that you can control EAX as a 32-bit value. Here, EAX is 1. So you look at it initially and you're like, well, I don't know, like, but then you'd need to look at the other 28 bugs in this bucket and find out what kind of spread you have. Like, if you look at them all and all the EAXs are 1, then you don't maybe throw it in the bin, but it's more or less like crap. Whereas it turns out with this one, there is quite a spread, so it's actually kind of good. So the classification goes with each bug, right? The classification does not go with the bucket. So if you looked at another one in this bucket and it had a different EAX, then that would be rated as exploitable, like this one. So this is the kind of thing that makes your mornings bright, where you've got like a value that's pretty much straight out of your fuzzer in EAX, which you're then calling. So that's like happy, happy days. So the other side is like, so these are good, but you need to like troll through. The other side is, what about when bang exploitable gets it wrong? Like this is a fail. So probably not exploitable because it's a read AV near null. But those of you with rudimentary assembly skills will look at the ESP and the EBP here and go, that doesn't look good. And then maybe look at the assembly and go, that doesn't really look good. So the stack registers are blown and it's running junk. So as a null pointer, like, these are the kinds of null pointers that are nice to have. I would imagine that there are several people who'd like, yeah, well, it's a null pointer, but I'll take it off your hands if you want. And the problem, like, for if you're like on offense, the problem is that bang exploitable is, like I said, only looking at how we got here. It's not looking at all at what is the state now, which is potentially something that at the moment has to be done manually. I could write some like really dumb heuristics, which I intend to do with, like, you know, grep and stuff, because it doesn't take much to replicate what I do when I'm lessing through the summaries, but it just needs to be done. Here's an epic bang exploitable fail. This is when I crash words so hard I actually break the debugger. That's awesome. You can see again, like, EBP's blown, so something has already gone wrong. And ECX and EIP are the same, which sometimes is like, you know, happens naturally, but is often like a sign that there's some awesome hidden there. And the fact that, like, bang exploitable, like, faltered when it tried to disassemble is, like, fantastic. So a lot of the bugs that I had where my parser, like, usually I parse out the machine parsable output of bang exploitable, and I had some bugs where it didn't parse properly, and I was initially thinking, oh, well, it's just something. But it turns out those are all awesome. Like anytime I don't get the machine parsable output means that the debugger's gone wrong, and that means that it couldn't disassemble, which is automatically, effectively means it's running junk. So almost all of those are worth looking at. And yeah, the ka-ching. Like this is where it should say like above exploitable. Like 0101, that's like straight out of my fuzzer. It's one of my binary corner cases. So basically I've found a please set EIP to this value structure. And that's nice. Like if you're going to start exploiting word bugs, then this would be like your Tinker Toys. But you know, crashes that cool must be pretty rare, right? You know, how often would you really get like full control of EIP? And you know, not that often, just like 700 or 800. That's the ones in red, where it looks pretty much like it's taken corner cases straight from my fuzzer. The ones in purple look like pretty much Unicode text. The ones in green look like ASCII text. And the rest are probably bad as well, but they're all funny. Okay, that's my 30-minute warning. So yeah, there's some bugs. Unfortunately, the only way you can now collate these is by going back through stack trace, because it's no good looking at the EIP anymore to collect them into issues. So you've got to go back and look as much as you can at where the bug came from. So you might find that like 30 of these came from one issue, which you can like kind of isolate by stack. But in a lot of these cases as well, the stack is blown. So you've got a problem where you can't even work out where it came from until you actually open it in a debugger. Then you can go to where the stack should be and try and like stick it back together with sticky tape. So yeah. Now all of those offsets, unfortunately, because like, well, I wouldn't say I'm a nice guy, but like I'm not a complete evil bastard. All of those offsets are now sort of dead-ish, so they're on death row, so I wouldn't bother trying to like go and exploit them. In the spirit of coordinated disclosure, they don't call it responsible anymore. Tom? We have now responsibly disclosed the bugs to Microsoft. And next we're going to talk about like my crazy research, which may or may not be useful. But are there any questions on just the bugs? Yo.
Do you often find it useful to tell Microsoft about something just so it stops getting in the fuzzer's way?
That is an awesome question. It's like, do you like to like disclose bugs to get rid of bugs that you see all the time? We already have, and they don't fix them because they're chaff and they make life harder. There are at least 3 crashes that I see all the time. Between those 3, I've probably got 40,000 of the 60,000 you saw. And I just like bin them because I know them. In other cases, I think that they deliberately make it fault. Like it's like, whoa, something wacky is going on, like read null, read null. Again, to make it harder for attackers to get to the real bug, which is an entirely valid strategy in my opinion. So yeah, but it's a very good question. Cool. Okay, crazy research time. This is all his fault. Dave, Justine's husband. So we're talking in the back row in Taiwan. And he's like, oh, I got one of my Dave ideas that I'll tell you, and like, then you can go away for a year and see if it works. So the idea is you take each basic block and number it. You get a run trace basically. So you run the program once with the file and once with the template. So that gives you 2 signals, right? NSA guys are like wacky about signals. And so once you've got those 2 signals, one of the clean file and one of the crashing file, you can look at them and do interesting things. And he's not really sure what they are, but you know, maybe like subtractive frequencies or maybe like a hidden Markov model or a neural network. Okay. And like make it tell you something. So
Analysis will save the world.
exactly. So the first thing you got to do, I guess, is to like get your run trace. We initially used Dynamo Rio, which is super fast and has like a nice clean API. It's horrible to work with on Windows. Like it needs CMake and MSys and all kinds of stuff you really don't want to be messing with. And then it like just stopped working for no apparent reason. So we gave Dynamo Rio the finger, and we're now using Pin. Pin is a weird looking API, and it's a little slower, but just because of the difference in the way it works, which is much more complicated than I'm going to explain here. But it's more reliable, it's easy to build tools, and it's cross-platform. It also is apparently what all the cool kids are using. Like I know Immunity are using Pin. Pin? You using Pin? No? Okay, at least, well, half the cool kids. So I would recommend if you're going to get into it, then Pin is probably a better bet, in my opinion. The run trace side was actually written by the Grug, who's like in another room right now talking about GSM. So he's like my go-to write this C code for me guy. So once you get the run trace, you run into some problems. So the streams of numbers are really, really long. We're talking like gigabytes of dump. Fast Fourier transform and hidden Markov model were red herrings. Neural network was just like a dumb idea. The hidden Markov model, right? Like we can directly observe the state. So trying to guess it from a hidden Markov model turned out to like not really be a good idea. And you'd be surprised, well, you probably wouldn't. Visualization, which normally saves the world, is very unuseful. Like, here we go. Like I scanned this with a barcode reader and looked to see if the bug came out, but it didn't. And here we go. Like, you know, imagine that one of these edges is red. That'll like tell you stuff, right? So yeah, visualization, not so good. So Dave did actually have one other awesome idea, which is like, oh, you could just use diff. Like 1973 still works, but the sequences are like psycho long. So even if you had a diff, you're like going to be like paging through a multi-gigabyte file, so you cannot read that effectively. And like computer heuristics for like, oh, this looks weird, are beyond my ability. Like there are some guys that are doing like cool stuff with graphs and like taking differences for bug localization, and I'm sure it has potential, but I can't make it work because I'm not smart enough. So I just thought, okay, well, so here's the thing about code, right? It's like very, very structured. There are long sequences which are going to be repeated all the time because like, you know, like go to this object is going to be represented as like one string of assembly. So I can compress that with hierarchical grammars. So I stole like an algorithm from some academics that did all the hard work. So say you take a nursery rhyme which has got a lot of structure, and then you apply this algorithm, the Secateur algorithm, and you compress it from that to, what's that, 13 bytes, which is cool. And the reason it's hierarchical is because if you look inside the rules refer to other rules, which gives you huge, huge, huge compression. So now if you had to diff that nursery rhyme with like a 1-character change, most of these bytes would be identical, and then the changed characters like stand out like a sore thumb. So I saw that initially and I got like super excited. Then came the long cold winter of like it doesn't work. The grammar for the algorithm is generated on the fly because the way the academic guys wrote it is awesome. It's linear time. So whatever length the sequence is, the time is linear, which is fantastic for very long sequences. But because it's generated on the fly, if you run it over 2 different run traces, the grammars are different, which means you can't compare them, obviously, because it's like apples and oranges. So I had to write a recompressor. Like I had to compress the first one, then keep that grammar and write a tool to compress the second file with the same grammar, which is less efficient, but they can now be directly compared. So like the nitty gritty is probably boring. So anyway, I wrote a recompressor that converts it to a tree, which is a computer science thing. I'll use science. Then I apply the same grammar to the second file. So now I take all transitions from address A to address B, and I index those. Each transition gets an index in a database. So then that index of tuples, the tuple sequence, gets compressed. The variant also gets compressed. And then I diff them, like just with sdiff, and it's like unbelievably fast. And then I go back to the database from where I took the trace, and I mark it up with some interesting info. So those of you that have seen my presentations before may be familiar with my annoying, hard-to-read green screen demos. And so now we have another one. How's that for size? We can go bigger? We can go bigger. Okay. Everyone read that fine? No. Okay, good. So what we're looking at here are the diffs converted into chunks. So the first chunk is like chunk 0. These are unchanged because, you know, it's like the loader. Starts at 0, goes through to call or ret number 1743, and compressed, it's 131 symbols long. The first time we hit a diff is here at like chunk 1. So rule number 20, or which could refer to the longest set is, I think, like 90,000 calls and rets, like 90,000 transitions compressed to a single rule. In this case, like rule 20 contains 80 fully, like when fully expanded, contains 80 transitions, and it's slightly different because, you know, there's like it's a bit longer. So if you feel like expanding all of those out and diving in, you'll like very rapidly go mad. It turns out that runs diff a lot more than you might think, like really a lot. Like if you run the same file, it'll also diff quite a lot. So you've got to be a bit selective about the stuff you're looking for. So I'm just going to press space now. This is the best demo ever. We need to shrink. Okay. So now these ones that aren't rules are transitions from A to B. They're not marked up as a module, which means they're either dynamic code, or this might actually be like in winword.exe. I don't know if for some reason it's not in the module list. The 1 is really interesting. The 1 means that this is the first time that transition has been hit. So this is where this is different from a graph. I have full sequence information available. So not only do I know the edges that were traversed, I know what order they were traversed in. And we'll come to why that's cool perhaps later in our mystical journey through green screen. Something interesting. Okay. Now the big arrow, like there's a small arrow and a big arrow. The big arrow means that this edge did not appear in the original file. So automatically that's now more interesting to me than the plain transitions, because this is like a transition that wasn't taken when it ran the non-faulting file, but was taken when it ran the faulting file. But it turns out that a lot of these dynamic addresses just change, like all the time. So once you like leaf through a few of them, you find that they're not fun. And I still need to make that smaller. Okay. So again, like annoying. We're getting closer, right? We're moving from an address in MSO, so we're in module space, but we're going to another one of these dynamic duvas. So we can see that like it's the same address, but it's just gone to a different whatever that is, say it's a dynamic address, and then come back also to the same spot. So not fun. This is why it's like, in my opinion, would be really complicated to try and do this automatically, because I can look at it, right, and say, oh, that's nothing. But how do I like write an algorithm that says, oh, that's nothing? Whereas you can see that code is basically identical, even though it's popping the diff. This is also where it's like a lot more complicated to do it with WinWord, which is massive, than like to do it for a POC. So, to cut a long story short, if I can remember how to use less, tick A, okay. So at chunk 285, so we're now 11 million calls in. On the right hand side we can see the first time we've gone from a real address, like an address in module space, to another address in module space. And that did not happen in the original file. So this might even be the bug. It's probably not. but it's like a good place to start. You can like start to see, oh, maybe I should like have a look at this particular offset. And this is now where the 1 becomes cool, because I know from the database, it's not on the screen here, whether that's a call or a ret. All I need to do is to break on MSO plus 55 F67, and the first time the transition comes from 55 B3A, whatever the hell that is, I'm in theory at that spot. I've like replayed time, which means that once I've broken there, I can inspect memory, I can see where my input file is, I can see like what's gone wrong, I can have a look at the disassembly, because I have the sequence data. And that's kind of cool. It gives you like potentially a tool that you really want as an analyst. Like it might not help at all, like it might be impossible to localize the bug, but you got to remember you don't always need to localize the bug. Like these 010101s, like no one's going to give a shit except Microsoft where the bug is, because you've already got like EIP control. It's the other bugs where you need to understand the bug in order to work out if you can control. So some of these you won't need anyway. Yep.
You said that this might be the bug, but probably isn't. Sort of implies that you get quite a lot of things worth looking at, sort of false positives, if you will, that you need to.
Right.
So what's the, for a bug you ultimately end up finding that's really exploitable, how many revisits do you have to do to a particular transition that looks suspicious?
Right. So like
100 to 1, 50 to 1?
I don't have those numbers. I am actually nowhere near smart enough to actually exploit word bugs. I'm also too damn old. So like that's for exploit monkeys. The tool is like designed to be a leg up. So we like the idea is that if I give someone a bug with this trace with like a few things like, hey, you might want to look at these 20 functions, then that's going to be way more valuable to them than say, look, here's a file, off you go. Because like when I first started manually analyzing them, like just to get to where stuff went wrong turns out to be impossible. So for me, I don't know whether you guys agree, the two big remaining problems in fuzzing are how the hell do we localize the bug, or how do we know if we can control it? So the first one is localization, the second one is taint analysis. So I'll be going to Charlie's talk right after this to look at taint analysis, and this is like a bit of a vague stab at localization. But the thing is, like, this is like number 11 million, and so this is the first divergence of control flow, and then there's like a lot more code, right? Like a massive, massive, massive amount more code. If we go to the end, we're millions and millions of calls after that point. So that's why you can't just like go, break, ooh, that looks interesting, break, yep.
So, Ben, in terms of trying to localize, so you're saying, I already have kind of a file that doesn't have an exploit. I know I already have an exploit. So this is all just trying to figure out, okay, once I have these exploits, here's how I localize.
Yes.
Easily you could go down all these different paths and you just had a different input file. That was also a good file, but it took you down different parts of it.
Sure.
So it'd be no help at all.
Yeah, but because I'm taking the same file, like with the change, hypothetically, many, not all, but many of the control flow differences should be based on the different input. There's other stuff you could do, which like I'm not going to go into, but there's a lot of different ways. The hardware analysis guys, like I was talking to Yob de Haas in Malaysia, and the hardware analysis guys have this problem as well. Like they're looking at power signatures. They've got an external Oracle, and they change the input file all the time, and by looking at the power signature, they can like subtract stuff and eventually work out where there's trouble, which I think was where Dave was going with the frequency analysis thing. Like if you ran like many different changes and then subtracted out or averaged out all the differences, you might get something as well. But I just haven't done that.
If you did 10 clean files for every first file, and then somehow subtracted the commonalities, the different common differences, if you like, from the first files, could that focus you in a bit on the important divergences?
Yeah, right. That's, I think, what I just said.
Yeah, that was the point I was, trying to make. You actually need a collection of files.
This is awesome.
The original. Yes. Even though you found the exploit file, it may be going down all these different paths because they're legitimate paths. You just happen to put the right parameters in across the different
Well, they are legitimate paths. It's in the module, right? It's a path that's supposed to be there. But the thing is, like something that we changed made it change control flow, and then later, after it changed control flow, it went wrong. And then, so if you want to get to the root cause, then presumably the root cause will be sometime before a major divergence. There will be some false positive divergences, but the root cause you're looking for, if you want to understand the bug, will be before one of those. You know, it's going to be like a branch or whatever, and then it's going to go wrong.
Does your run tracer modify the environment at all? So when you're running these test cases, is there any concern that the output you're getting here is somewhat tainted because of the run tracer modifying?
Yeah, right. So the question is like, this is like the Schrodinger's cat thing, like by run tracing it, am I changing it already? Potentially. I don't think so, because of the way pin works. It's pretty much running the same code in the same place. The memory layout will be slightly different because like there's a DLL that's been injected. So it is slightly different, but I don't think it's different enough to matter. I could be wrong, but no, I don't think so.
Okay, what's the slowdown you're getting on your test cases that are causing seconds with your run tracer?
Yeah, okay, so the question is how much slower is it to trace it? The answer is I don't care, because I'm only tracing a tiny percentage. I'm only bothering to trace files that already look like they're worth spending time on. And the post-processing to generate this kind of stuff, because it's in Ruby and I suck, is like 3 or 4 hours anyway. So whether Word takes like 30 seconds or a minute is like not important to me at all.
I just wanted to compare notes.
Yeah, I think it's, the pin guys say it's in the order of like between 2 and 10. But even if it's 10, like, don't care. So if I quit that, you could also do that and just have a look at all the stuff that's changed, which would be another interesting thing to do. Like, I'm all into like doing like advanced crash analysis with awk and grep. So there you've got like all of the control flow differences. So you've got all the places that you might want to look for a potential bug. Yes?
You could run the tracer on 1% of all of your test cases, even the non-exploitable ones, and use that to determine which test cases caused something interesting to happen, and then use those as starting points for your budget later. So you get to different parts of the code.
Okay, so I could run the tracer on some of the test cases and then use those as re-input into the fuzzer.
To decide which ones to use as re-input.
Yeah, I could probably also do that without the tracer though, right? I could just take like files that looked like they were almost interesting and remutate those, which is one of the things that I'm like doing. The other thing which is also kind of interesting is like if you're running what I now call Miller fuzz, like Charlie's now like live forever in script form. Like Charlie's fuzz sprays random shit in random locations all over the file, but it makes many, many changes. So say you get a crash, like my fuzzes change something quite small, like it'll change a few bytes. So if you get a Charlie crash, how the hell do you know what it is that caused it to crash, right? You diff it and you've got like, oh, there's like 600 changes, yay. And so what you do is you take it and you revert those bytes one by one, resend it through the harness, and eventually you'll get down to 1, 2, 3 bytes that actually cause the crash. And that can be done automatically as part of the process. Yep.
For the feedback he was talking about, how did you say you were doing without tracing? How were you figuring out which files were interesting and just one that caused itself?
Okay, so like how I don't do this, but how would I pick which files to put back in for remutation and feedback?
Oh, I thought you said you already did.
No. I would just pick crashes. I don't, like the thing I don't understand is how tracing it would help, right? If it's crash, then it's a crash. I take it like and it looks interesting, then I can use it for remutation. Like if it's not a brain dead crash, it might be interesting to take that. Like if it's like already a win, then I wouldn't do it, and if it's already a dead loss, I probably wouldn't do it. But if it's like in the middle, I just pick them out. Like I look at the summary and there's a, that almost looked good.
Yeah, I think a crash is easy.
Is that like until question time or until like you wrestle me off stage? Okay. So 5 minutes until I'm wrestled off stage, which now makes it officially question time. Like I know it's been like question time for like the last 15 minutes. Yo.
I put on to climb this and I overestimated my ability to navigate, so got here really late. But your test cases with the OLE, are they strictly opening these bad files, or are you doing more than that with the files?
I just open them. If it doesn't crash on open, then it becomes uninteresting to me. There are some areas where I thought about looking at, like you could fuzz just OLE calls, right? You can do anything inside Word with OLE. So you can get the method, scriptomatically determine what parameters it wants. And so you can just like call random methods with random parameters inside Word, and surely something would go wrong. But it's not cool. Like a bug that owns you as soon as you open a Word doc is cool. Anything else is not cool. So that's all I'm looking for.
Okay.
Yep.
Do you have a sense of, sort of guesstimate sense of the reliability or the crashability of opening OLE2 style files to opening the newer docket, the zip type files?
Ah, yeah, right. No, I don't have those numbers yet. The only ones I've looked at are .doc and RTF. RTF is surprisingly easy to crash. I've not yet looked at the zipped up stuff. I've got code that I'm almost done writing. It's not that hard, right? You know, you unzip it and there's a bunch of XML files, and then you take anything that looks like a binary blob and you mess with it, then pack the whole lot up, which is much less complex than a lot of the stuff that I do now. It's just I haven't done it yet. I would imagine that it's not going to be that much harder though. Tom may disagree, but yeah.
You mentioned that it might be a sign of exploitability if the EVP and ESP are inconsistent, but this wouldn't work if they're using frame pointer optimization, so the EVP is just like a general purpose register. Have you run into that at all?
I haven't, but if ESP's blown, then it's funny. Like, if I don't even know if they use like frame pointer optimize, all the assembly I've read seems to indicate that they're not, but you know, ESP I think is a pretty sure sign. Like if ESP is like FFFF something, then shit's gone wrong. I should mention, if you're grepping through bang exploitable things, like good stuff to look for is anything that says unknown symbol, because that means it's like out of module space, and that's good. Look for move byte pointer EAX AL, because that's 0000. The opcode for that is null null, and that doesn't come up that much in real life. And yeah, obviously like AVs at the instruction pointer, and then you just like grep through and look for shit that's not proper ASM, which obviously you'll be able to spot instantly. No more questions? Shit, that was easy. All right. Awesome. Thanks, guys.